you that perhaps wouldn't normally join us in person. Last month we had over 100 of us at Keele University in England. For those of the international guests joining us tonight, that's in North Staffordshire, so about halfway up in England, just outside of Manchester, between Manchester and Birmingham. So to tonight's talk. So as you may have seen from the programme, tonight's speaker is Dr. Ronald S. Gamble Jr. And I'll very shortly introduce you to him. But just a couple of house rules for those that maybe haven't joined us before. You'll notice there is a Q&A and a chat function this evening. We typically run the talk for about 45 to 50 minutes, and we'll have about 10 or 15 minutes Q&A at the end of that particular talk. So if you have any questions for Dr. Gamble as we go through this evening's talk, please pop them in the chat or the Q&A. And myself, Stephen, or Sharon, who's in behind the background here, will pick those up and we'll make sure that we post those to Dr. Gamble at the end of his talk. There's no opportunity to use your microphones tonight because we're expecting over 100 guests. So if you do have any questions, just pop them in the chat. For the eagle-eyed amongst you, you'll notice that we also have Stephen with us again this evening. Stephen is our British Sign Language interpreter. So again, if you've got friends or colleagues that might require that support, then please make use of it. The talk will also be recorded and posted on our IOP West Midlands YouTube channel. So give it a few days. It is half term coming up here, but as soon as we've got that recording sorted, we will make sure that goes up on our YouTube channel. So with no further ado, I'm going to introduce you to our guest speaker this evening. So as I said, our speaker is Dr. Ronald S. Gamble Jr., who is a theoretical astrophysicist at NASA Goddard Space Flight Center, researching the energy emission processes of relativistic jets from active galactic nuclei and their connection to supermassive black hole rotations. You can see, as a mere nuclear physicist here, I'm already struggling with that introduction. He is currently a CREST 2 visiting assistant research scientist at NASA Goddard Space Flight Center and the University of Maryland, College Park. Accompanying this, Dr. Gamble also has 7 years experience in academia as a physicist, mathematician, computational science instructor, and as a curriculum developer. His experiences span across multiple industries, including higher education, space and defence, and the arts. Dr. Gamble holds professional memberships in the National Society of Black Physicists, the National Society of Hispanic Physicists, and the American Physical Society. Just to finish up, which I always find is a really nice, interesting thing beyond the world of physics, Dr. Gamble tells me that he's also an established oil and acrylic painter, graphic designer and illustrator. So with no further ado, if we were at Keele, we would give you a very warm North Staffordshire round of applause. But since we can't do that, it will just have to be me, Dr. Ronald S. Gamble Jr. Welcome to Keele, and I look forward to your talk this evening. Thank you.
Thank you, thank you, thank you. Thank you for the introductions and the kind words. I'm gonna kick it off here and go ahead and share my screen. All right. So like Scott said, I'm Dr. Ronald Gamble. I'm a theoretical astrophysicist at NASA Goddard. And today we're gonna be talking a lot about black holes and space-time and all the fun stuff that's kind of in nature of dealing with relativity. So this is, I know if you've heard of black holes, if you studied them, this is not going to be a large mathematical talk. There's a bunch of equations behind me, but that's not the gist of the talk today. It's going to be very animated. I'm going to show you, the physics behind black holes, where relativity came from, what is relativity, the special general relativity, and then a piece of my work that I'm working on also. And so, promise there's not going to be a lot of equations, there'll be a lot of pictures, animations, but you will, at the end of the talk, you'll know quite a bit about black holes, and you'll have some nice conversations, around some beer or coffee or something like that. So let's get started here. A couple of introductions into kind of the nature of black holes, the nature of space-time and relativity, right? Like I said, I'm a theoretical astrophysicist. You can look up some of my work online. You can find me on the NASA page, social media, my website, email. Feel free to reach out, and I'll share that information with you at the end of this talk. But I generally use general relativity theory to kind of describe the physics around supermassive black holes and the high energy environment around the black hole. So we're talking very near the event horizon, right? That's kind of the boundary for our observable universe, where it's that point of no return. If you cross it, you can say goodbye to your family because you're not coming out. But if you get very near it, the physics gets very weird. We get very weird physics in that environment. It's highly, highly curved. We're going to touch on what curvature of space-time means in a second here. But the matter energy around the black hole, very near to the horizon, becomes very erratic. It becomes very sporadic in nature. It becomes very spontaneous in some of the processes, and very, very energetic. So when we talk about energetics, we've got some nuclear physicists in the audience, some possibly some theoretical physics, some experimentals. We're talking about very hot, very energetic, very bright matter, right? So we're going to touch on an object that I study in nature called relativistic jets, and those are some of the objects that extend very, very long. Some are short, but very, very long objects. They extend out to a few parsecs to 1,000 parsecs in length. So 1 parsec is about 3.26 light years. So we're talking millions and millions and millions of miles out. So it can extend very, very long distances. And so they're very bright objects. So now, and I practiced putting together exactly what I do in one sentence, and I theorize scientifically plausible predictions of new physics describing black holes, quasars, which are active galactic nuclei, types of galaxies that I look at, and relativistic jets using complex mathematics and analogies to other occurring phenomena in nature. So as a theoretical physicist, I kind of piece together, I make observations in nature, and I piece together analogies that I can then translate into mathematics, use known theory or extend known theories that we have to then come up with an interpretation and prediction and a theory or a hypothesis to what new things we can kind of figure out in nature. What is nature actually telling us, right? So what are new things that we can figure out based off of known observations and theories? So just a little bit about the history of gravity. The very first, I would say about 1586, and I'm gonna go through this timeline real quickly. That was the first interpretation of 2 objects dropping of different masses and accelerating at the same rate. So if you've seen the bowling ball and feather test on the moon, that's what that's testing. And it's going back to 1586. So this is pre-Newton in the 1600s, right? So this area of physics has been around for a very long time. And there have been leaps and bounds, as you can see, right? To where relativity, where gravitation, where black hole science, black hole physics comes from, right? As a collective body of knowledge that, the world has kind of contributed to, where does all this come from? So we can see about 1876, that was our first collectively as humans per se, that's when we first made the interpretation of the motion of matter has to deal with something about the geometry of space. Not necessarily, we didn't have a concept of space-time per se in 1800s, in 1876, but we had a general idea of points in space. So relative to points in space, what's the motion of matter? That was about 1876. So if we keep going and we keep moving on, we get this, this Austrian-born scientist. He was a pretty popular guy in the 1900s. You might have heard of him, Albert Einstein. He did a lot of things. You've probably read about him, but in about 1905, that was when his special relativity came out. If you've seen E equals mc squared, the popular equation, that 1907, that 1905 paper, though, that's when that was really popular, and that came when he theorized those equations. 1950, we got about general relativity, right? So we're going to touch on all of these things in a few seconds here. I have to mention in 1973, Meissner, Thorne, and Wheeler came out. That is the gravity Bible. If you're in relativity, if you study black holes, don't disagree with me. That is the gravity Bible. Anybody will tell you it's a very thick book, but it's been around since the 70s. And so again, then advancing up to 2019, we see the Event Horizon Telescope giving us that shadow of the supermassive black hole M87. M87 is one of the objects that I study currently right now. And we're going to see an animation of some of the simulations later on. And so now what's next? Who knows? We might have time-dependent solutions of the Einstein field equations. We might have quantum gravity. That's on my bucket list. We might solve, the galactic velocity dispersion problem that's happening right now for dark matter halos. Warp drives, it's again on my bucket list, but who knows? So this is where the field is going. This is where gravitational research is kind of headed into. And of course, there are some alternative theories that we're going to see in the latter half of this talk, but these are some of the unknowns. If you're going to look up what are the unknown problems in physics, what are the unknown problems in relativity, gravitational physics, these are some of them. Warp drives maybe a little bit off, maybe a little bit sci-fi, but we can all dream, right? And so now, looking at examples of what's actually gravitational physics, how do we study this, right? So we're looking at either stars rotating around black holes, we're looking at matter accreting around black holes, we're looking at these things called relativistic jets. Oops. These are the bright objects coming off at the very centers of galaxies. And so it's a combination of different methods, different theories, different techniques. And then it also requires an advancement of technology, right? So LIGO turned on, gave us some first results for testing and observing gravitational waves in about 2015. I was lucky enough to use LIGO data in my dissertation in 2015. 2019, we got an EHT image. 2030, who knows what happens? We're expecting LISA is the next generation of laser interferometer gravitational wave observatories to go up. That's both a NASA and the ESA, the European Space Agency collaboration. So I'm excited for that to go up so we can get some great results on that. Should be able to see some very, very good observations of gravitational waves with that. So it's an example of what do you actually do in gravitational physics, right? Well, there's another piece to that. If you're not an observationist, if you're not in experimental work or technology, then you're doing theory, right? So we're using things like numerical relativity, we're using analytical theory and extensions to general relativity. That's an animation from my dissertation work of what happens to the internal structure of a black hole as you increase the speed, right? So as the spin gets faster and faster, how do the black hole space, how do the structures deform, right? So you can see the first slide there is a Schwarzschild black hole, no spinning. The very last one is what would a naked singularity look like if we extend that spin parameter past 1, right? Past that unitary ratio, if we get into extended hyperspins for black holes, what's the structure of space-time look like for a naked singularity? We're not touching on naked singularities today, but if you got questions, you can send me an email, you can reach out to me, we can have some further conversations there. To the right on the screen, that is a toy model of M87. So we saw M87 before with that EHT image that we're going to see again, but this is a numerical toy model. So this is 2 scale, right, of M87. We can see the accretion disk. This little halo sphere around this black center sphere is the ergosphere. We're going to touch on that again later. That's kind of where our maximal rotations are happening around the black hole and what's the structure looking like. The purple conical geometry, right, is a representation of the jet, right? So we can see the jet coming off both in the top, the North Pole and the South Pole of a black hole. A black hole is spherical. It's not a funnel that you might see or a whirlpool that you might see, but that is a mathematical illustration of what a black hole is. A realistic illustration or depiction of a black hole, it's spherical. It's an oblate spheroid. So it's kind of the same shape as our Earth. Our Earth's an oblate spheroid. It's not perfectly spherical because it spins on an axis. Now, images, you are looking at 2 supermassive black holes, even though this is an image of a colliding galaxy. This is a black hole binary, but they are also galaxies smashing together over millions of years. So these are some of the objects that we study at NASA. Some theoretical astrophysicists study, observational astrophysicists study these, other astronomers study these, but you can see kind of the interplay, the interdisciplinary nature of studying black holes. You can study them both from the observational standpoint and studying the optical, X-ray, or infrared radiation that you see here. So this image is an overlay of all three spectra over here. And so it's an interplay of multiple areas of physics, multiple theories, multiple techniques, a lot of people coming together to give us an advancement of the knowledge of what we know as black holes. They are the most obscure, weird things in the universe that we know of. So now, kind of touching on, kind of getting in deep, diving deeper into the science here, right? What exactly is relativity? What is space-time? So to touch on some of the history of relativity theory, right? Again, we saw William Clifford. He suggested for the first time that we have some type of geometrical relationship to the motion of matter within space, right? So that's matching the relative motion of matter to some type of geometrical configuration of space, points in space, right? So you can see in this cubic structure, that animation, there are clocks at each point in that Cartesian grid, in that 3D grid, there are clocks. This is the best illustrative example of a four-dimensional space-time, right? So we got that in the very, very late 1800s, early 1900s, about a four-dimensional interpretation of space and time, coupling them together, right? Michelson and Morley, this is a classic experiment that you study both in undergrad and graduate. We're still studying it in the professional realms about, you know, the motion, the relative motion of the Earth with respect to what this thing was called in the early 20th century, about the luminiferous ether, right? So this is what they interpreted space-time to be. We had matter moving through some type of entity that it interacted with, right? So these are kind of figuring out, asking the question, you know, what are the things that go bump in the night? Yeah. But what, in terms of now, we're getting into, well, what actually is the night, right? So what actually is space-time per se? And so that was kind of the first interpretation of that. If you haven't read that paper from 1887, it's been years, I should say. Go read it. There's still some great insights into that paper, into kind of the philosophy and the logic of the way these gentlemen thought in developing the early stages of relativity theory, right? So of course we got in 1905, Einstein did his thing. And again in 1915, every paper he probably should have got a Nobel Prize for, but it would be crazy if Einstein won it 12 times in the span of like 50 years. But his work was very, very fundamental to most of the technologies that we have today. You can thank Einstein's general relativity for GPS on your phone. You can thank him for satellites, the motion of satellites in the air. Elon Musk can thank Einstein for sending a Tesla into orbit. That was relativity. So it's a lot of different applications we got from special and general relativity. So again, well, what does space-time look like, right? So without the clocks, this is kind of the motion or rotations in space-time. How does space-time curve? How does it quench, right? So you can see an artistic rendition of the curvature of space-time. To the right is your gravitational well. So that's that funnel structure that you commonly see in describing black holes, right? So this is kind of depicting the static curvature of space-time. So you can see this is kind of a rigid notation. We haven't included or considered a phenomenon around black holes called frame dragging. It's coming up really soon here. Without frame dragging, this is what the curvature of space-time would look like around a black hole or some object with mass, right? So now, general relativity, we're just going to skip right into this. Einstein put together a theory that was, in my opinion, very intricate, very intimate, very, in other words, beautiful. It was a beautiful theory that matched the abstract geometry, right, from differential calculus. This is Riemann geometry. You can go look it up. That's the tool that he's using here, describing the Einstein field equations. But he matched that with, okay, well, what is physics? What is matter energy doing in four-dimensional space-time, right? So we're looking at X, Y, Z, and time, right? Or that could be R, theta, phi, and time, right? Three spatial coordinates one coordinate of time, gives you 4D space-time. So we have an Einstein tension that kind of gives us an interpretation of how space-time occurs with respect to the motion or the configuration of matter energy. And also the contrary. What is the motion of this matter energy with respect to this curvature of space-time? So it's a very, very fundamental, very classic equation in theory. If you like to have headaches or something, or you want to hurt your brain, go read the General Theory of Relativity, and it's in original or in translated text, and then you'll have all these questions of space-time. What about wormholes? What about dark matter? Do we really know what's in the interior of a black hole? We don't yet, but there are some open-ended questions that you get. Some of the curiosity, right, for relativity in physics are kind of thought up and generalized in relativity here, right? So we're talking about 16, it's a set of 16 coupled nonlinear partial differential equations. And you can see the Greek letters are the indices on each one of those equations. For every component in our space-time x, y, z, t, we have a set of coupled differential nonlinear partial differential equations. So you can see all the math behind me. You can see that, yes, that's some general relativity behind me, and it's bonkers to try to do by hand. So sometimes we solve these on the computer. We use supercomputers. We develop simulations, parallel codes, high-end, very large codes to solve some of these equations to give us some very new physics that we're testing here. So kind of getting into, well, why geometry? Why is geometry such a fundamental aspect to relativity and gravitation? So again, we have this graphical depiction of space-time curvature. This is one of the best interpretations or graphical depictions that you're kind of going to see for space-time, right? Space-time is an obscure to abstract idea. We can't actually go out and collect, a morsel or a vial of space-time and then go test it in the lab. Space-time is kind of an abstract entity, right? It helps us do the math better. It helps us match the physics to what we observe in nature, right? So we're matching the mathematical theory to the observational data that we see. That's the benefit of space-time, right? So we can pinpoint your existence, for example, my existence as an event in space-time. We are currently existing in some configuration, some geometry in space X, Y, Z, and then at some moment in time. So you get your 4D space-time configuration. Another aspect or another phenomena around black holes that kind of modifies what we see happening in space-time is frame dragging. Frame dragging is the dragging of inertial frames. So we're talking about the motion of matter as it moves or rotates around a source of curvature or a source of strong gravity. Frame dragging. There's frame dragging around the Earth that we see today. We have to compensate for frame dragging in our satellite communication in GPS just to make sure that we aren't off by milliseconds, nanoseconds of information. So we can see light travels very fast, right? And our information is sent down from Earth up to the satellite and then back again very quickly also. So if our calculations or our approximations are off by a couple of seconds, that could mean catastrophe for some other critical infrastructures or things that require satellite communications down on Earth, right? The International Space Station requires very accurate calculations, and it interprets and it considers some very small contributions due to frame dragging around the Earth. So this involves rotating self-gravitating systems, right? So now, getting into why we're here, right? Black holes. Roy Kerr, which was kind of one of an unsung hero in general relativity. Thank God for Roy Kerr, because he developed what we know of as the Kerr solution or the Kerr metric. So this is the mathematical solution to Einstein's field equations that helps us describe the space-time around rotating black holes. So these are the astrophysical black holes that we see in nature, right? So we've seen that every black hole that we've seen thus far is rotating. Some have a disk, some have jets, Some have what's called tidal disruption events that literally shred whole stars or galaxies apart. You can go Google tidal disruption events, but the Kerr metric, in essence, is a vacuum solution, meaning that we're just talking about the space-time, about some curvature within that space-time. We're not necessarily talking about a dependency on the constituents of matter energy for that space-time. I'm just stating something is there, something's rotating, and this is the space-time that it generates or that it curves, right? So that's the Kerr solution for black holes. And it's only describing the local geometry of space-time of an axially symmetric rotating central mass with some type of spheroidal solution. So again, we're talking about spheres here, not necessarily funnels. So get the funnel idea out your mind and inject the spherical interpretation of black holes in there. That's the accurate description of black holes. And so now the key words here are axially symmetric. We're talking about things that spin on an axis. So if you look top down in this animation here, you're going to see a circle. Those are black holes. Black holes pull down, right, from a bird's eye view, are circularly symmetric. They are symmetric there. It's when we look at them edge on, right, from the disk point of view, that they kind of have some deviation from the top and they kind of squish due to rotations. So it's a weird geometry happening in black holes, but this is what we see. So we've matched theory with observation very well. So now to get in some of the mathematics behind this, right? So down below in gold, you'll see that is the Kerr metric. You can think of the metric as a ruler for space-time. How are we measuring distances in our space-time, and how are those distances changing with respect to other things that are moving within our space-time, right? So you can see, again, this is an example of some complex mathematics, but that is to the right, again, the toy model of M87 to scale of what the structure of a black hole looks like. So you're taking the mathematical equation on the left and you're translating into a model or some type of graphical depiction on the right. Both are accurate with each other. So there's a lot of things in between, going from the mathematical abstraction to the graphical or the simulated models that we see here, right? So this is what we're doing when we're studying black holes. We're taking the mathematical theory and we're making plausible predictions or models about what we see in nature based off of how we can use math as a tool to interpret what we see, right? So mathematics here is more or less a language that we use in studying black holes. Now, I'm going to show you two different types of black holes. There are 4 types of black holes, but 2 here. One without spin is called a Schwarzschild black hole, right? So you've heard of possibly the Schwarzschild radius or Schwarzschild length. That is the point of no return in a black hole. So this orange, this red circle that you see here, right? That describes our Schwarzschild radius. That is the surface for a non-rotating black hole. That's the surface of our event horizon. If you cross that, you're gone. We can't get you back. You can't call home. You can't use a lifeline. You can't throw a tether out. I can't send you in on a fishing line. You are gone. We can't get you back. As far as our physics knows and what we've interpreted and tested and seen, that is the point of no return. It is completely black. We can't get out of it. And it takes all of space-time and it squishes it down to what we call a singularity. Now, the very weird part, as soon as you rotate the black hole mathematically, you go from this singularity, this one point, to a ring that's at the center of a black hole. So at the centers of rotating black holes or Kerr black holes, right? These are black holes with spin, but no charge, okay? Schwarzschild black holes, no spin, no charge, very basic entities. But the ones we see in nature are the Kerr black holes. The space-time surrounding the Kerr black hole is very complex, right? So we can see ingoing and outgoing motion within this black hole, right? So this mathematical solution admits 2 types of black hole solutions here. One that's pulling in matter energy and one that's expelling it out. So if you've heard of the idea of a white hole, that is more or less the opposite polarity of a black hole. So instead of pulling matter in, it spits matter out. That is the blue arrows, this blue currents, right, happening on the left side for the curved black hole. The white ones, right, are what we actually observe in nature for a black hole. It's pulling in matter from all directions. You can see in the black hole structure, the internal structure, we have what's called an ergosphere, right? So that's this torus, little donut-shaped geometry surrounding the black hole. That is where frame dragging, that is where other phenomena called the lens-Thurling effect happens. There's another phenomenon called Mach's principle that happens there. So all these other rotationally induced phenomena happen in the ergosphere. This is where space-time is being sloshed around at very high speeds. This is where the closer the interior regions of the accretion disk exists. This is also kind of where it's a weird zone that overlaps with what we call the photon sphere. So the photon spheres we're going to see in animation from EHT in terms of black holes and what we can observe. That is the light, that's the closest light that we can see around the black hole. Anything beyond that is black. We can get photons out, light that can't escape. Space-time is literally expanding, it's squishing at a rate faster than the speed of light. So light cannot escape. That is the speed limit to the universe, light speed. You can't go any faster than that, according to our current theories. But the weird thing that happens is that space-time stretches at a rate faster than when light can escape. So the escape velocity for the interior of a black hole, according to relativity, is at infinity, right? So it takes an incredible amount of energy for you to actually escape out of a black hole, if you could. And I put that in air quotes and say, if you could, because again, we're learning new things about black holes. Maybe one day we might be able to travel to one if we have something like warp drives or we have some advancement in space travel. But as of right now, the closest one, the closest supermassive black hole to us, and these are black holes that are billions of times larger than our sun, is Sagittarius A star. So that's at the center of our Milky Way galaxy. You can see it, we point our telescopes at it, it's very bright, and there's a lot of matter circling around it, and it's very high energetic. So there's a lot of things happening around black holes. So again, this is what EHT on the left has simulated, right, based off of Einstein's equations and the theory of general relativity and observations or seed data that we've observed from black holes. And then on the right is what they actually saw. So what you're seeing here, that's the matter, right, circling around the black hole within the photon sphere. That is the closest, as of today, in terms of technology standpoint, that we can peer into a black hole. That's the closest that we can see. So we're kind of looking out of our bedroom window here on Earth, right? And we're kind of peering just down the street to see what we can see at a black hole. We can't quite see exactly what's going on inside of house black hole or something, but we can see what's going on in the backyard, right? So that's the light that you're seeing kind of in the backyard of a black hole. This is what we call the black hole shadow, is what you're seeing here, right? So it's a very, very accurate depiction of what we see in theory, both and in nature. So theory and nature, as of right now, they're behaving fairly well. So what we're theorizing in our mathematical equations is what we're kind of seeing in nature. Nature offers some hubbling corrections, I would say, to us theorists. Us theorists, we try to interpret what nature is doing, and nature says, you're wrong. Maybe change this sign from plus to minus. Do this here. And so we take observations, we trust that nature's telling us, a very accurate depiction of what's going on here, and giving us clues to update our mathematical and numerical theories for what we can see for black holes, right? So these are what we would call astrophysical black holes. So these are black holes that we can observe, right? So there are other types of black holes that we can't observe. Those are more or less not what we're categorizing here as astrophysical black holes, but more or less these are what we are talking about in terms of astrophysical black holes. Now, are there extensions to general relativity theory? Yes, there's a bunch of other theories that we can see. Metric theories, this is where general relativity lives, right? But there are other theories called biometric theories. There are scalar tensor theories. So this is now, we're going into the realm of like string theory. We're going into realm of kind of the multiversal theories, M theory, Gauss-Bonnet gravity, there's Lovelock theory, there's FR gravity. So that's taking the Ricci curvature, the space-time curvature, and using it as a function that can be modified later. So there's a lot of different theoretical interpretation of what's going on for black holes, but there's a finite amount of variables that you need to test for to make sure your theory is actually correct with what we've seen already in nature, right? So some theories can do what others cannot. Other theories can't do what general relativity does. And so, but this is the broad general knowledge of how we're advancing the field of gravitational physics and relativity in space-time. And at some point, quantum gravity will come up also once we complete that theory. So this is kind of an overlap. You might have seen quintessence as a buzzword here. But again, these theories in general, right, including general relativity theories, they try to make interpretations or hypotheses for dark matter, dark energy, non-stationary spacetimes, where the space-time geometry itself changes as a function in time, right? The matter-antimatter hierarchy, inflation, cosmology. So we have all these other interpretations that we've seen in experiments that we've done, observations that we've seen that help us advance the field of relativity in gravitational physics. So now, how can we actually see some of these things in nature? Well, I study objects called relativistic jets. Again, so these are jets that are coming off of the very, very near zone of the black hole, right above the event horizon, and they're extending out to thousands, if not millions of parsecs, right? So this is the jet length here. The lifetime is on the scale of 10 to 100 million years, right? So these are very, very old, very long, very, very bright, very, very explosive objects in nature. So they're one of the most cataclysmic, most explosive and brightest objects in the known universe. They cover the entire span of the electromagnetic spectrum. In the red are parts of the spectrum that I study. So as a high energy theorist per se for astrophysical black holes, I'm looking at radio spectra, I'm looking at X-ray, gamma rays, cosmic rays, and then higher. So these are some of the non-thermal spectra that we're going to see out of the relativistic jet black hole connection. And you can kind of see what happens here, right? What's the physics involved there? What component of the system am I looking at, or are we looking at? We're looking at jets, the dust, the corona, relativistic beaming, and other things like that. So this is kind of an illustration or artist rendition of what a jet would actually look like if we were to actually approach one. The Blandford's-Nyack process, another mathematical theory that's based off of observation, is the theory behind how the jet gets emitted, right? So how are these jets being emitted? What's the geometric structure of the jet? What are some of the spectra that we see in the jet? And then, what future interpretations can we see from observing the jets and advancing the theory from jet emissions, right? So on the right, you see kind of a depiction that, or a model that I've put together in terms of, well, if we can't see the actual black hole because it's black, but we can see the matter circulating the black hole, then we can test and observe the plasma that's going around the black hole. So of course, when we're talking about plasmas, we're talking about very hot electromagnetic matter, right? So we have to look at the structure and the geometry and the dynamics of the electromagnetic fields. Around the black hole, you'll see that in blue and in red and in gold, the yellow there, you're going to see different configurations of magnetic fields for the jet disk black hole system, right? So these are some of the components of relativistic jets and supermassive black holes that we use, that it's our visual disposal to interpret the physics that's going on very near the horizon, very near what we call the jet launching zone, right? So that's a few Schwarzschild radii above the horizon and below the high emission that's within the jet launching region. So now, to kind of segue this, to kind of wrap this conversation up about black holes and weird stuff that we've seen, it's going to get a little bit weirder. My dissertation work, what I did in grad school, is I studied very intimately and very heavily, I picked apart Einstein's theory of general relativity, and I asked a few questions, very fundamental questions. What happens when the geometry of space-time is temporally, right? When it's time dependent and spatially dependent? What happens? What happens when, or if we, how can we, radiation be generated from a dynamic gravitational field? So we're looking at time-dependent gravitational fields, and how can we extend our interpretation of gravitational waves? So these are the things that LIGO has observed. These are the things that LISA will observe in the future when that mission goes up. Fingers crossed on LISA data, it should be exciting. But how are we looking for gravitational waves? And how can the theory keep up with some of the observations that we're seeing? And then the last two questions I asked myself in my dissertation work was, what are the consequences of this, right? What happens to the other side of the equation? The T mu nu, the stress energy tensor, the matter content. How does that vary when we're talking about these dynamic gravitational fields, right? And then can gravity be interpreted as coupling of three distinct different degrees of freedom when we're talking about the stretching and the torsion and twisting of space-time, right? So this is talking about interpreting space-time as some type of viscoelastic fluid now. So we're talking about space-time having physical attributes now that we can kind of test for in terms of, you know, going back, can we take the Michelson-Morley experiment and make a modern version of that in terms of testing the elasticity of space-time? Can we do that? So that was part of the theory that I did in my graduate work. You can go read it. It'll give you nightmares, but I went from the Kerr line element, right? So the Kerr solution, to talking about, well, that is in essence what a black hole is on paper. If you had one succinct equation, I'd probably write that one down for what a black hole is. And then you kind of ask yourself, well, who made this stuff up, right? That's what I asked myself. And then after a bunch of coffee, as I have right next to me, and other theorists will have a bunch of coffee as well, we get brand new physics out of that, right? We get brand new science, we get brand new physics, sometimes brand new mathematical interpretations, but then we have to ask ourselves, well, what is this? What did we just create? How can we interpret it? Does it match observation? Does it match something we've never seen before? Can we solve it on the computer and test for that? Can we run simulations using high performance computing, right? And parallel computing. So it's things like that, right? So that we get out of new physics, new theories. So we're advancing the field, right? That is what our dissertations are supposed to do. We're supposed to make a contribution to the field, and we're say, yes, I did something. And then we go out and we get a postdoc and we say, oh crap, there's more to do. And then we keep doing that, and we keep doing that. And this is how we get advancements in the field, as you saw in the timeline of physics, right? This is how we keep making advancements in the field and maturing the theory. My current work is focused on looking at those relativistic jets, but taking a more general relativistic interpretation of that. So that's using general relativity, that's using the Kerr metric, that's using space-time, right? And the mathematics and all the mechanisms behind that in interpreting what we see in these active galactic nuclei and the jets that come off of them, right? What we see around supermassive black holes and the jets that come off of them. What's the interplay between the two? What's the angular momentum exchange between the ergosphere of a black hole within and the photon sphere of a black hole to the jet? Is there a connection there? So part of my work is trying to answer some of those questions. Of course, it's a contribution to the field, as we say, but it will help generate new questions that hopefully other people can collaborate on and answer and ask, right? So that we can have new frontiers in general relativity and black hole physics. So just a quick look at what I have here, what are some of the mechanisms I use, some of the new techniques that Einstein didn't use back in 1950, but that we use today are called spinors. So anytime, or tetrad interpretation of relativity or your space-time, anytime you have things that are a little bit dynamic and you want to match that to observational variables, you use tetrads. It kind of helps to break apart, separate the 4D covariant interpretation of space-time relativity that we have, and it turns it into structures that are more easily consumable mathematically. They're easy to work with. And then we can take them apart and put them back together into other easily consumable structures for what we call spin tetrads, right? So when we're talking about frames that are spinning around, it becomes easier to interpret and make mathematical interpretations of things or develop mathematical theories now that we have a basis of vectors that's dependent on our rotations in space-time. We have now an orientable frame that we can say, all right, from this zero angular momentum observer, a ZAMO as we say, what is our relativity doing? What's our motion of matter doing? What's our space-time look like? What's gravity looking like, right? So it helps us do the math easier. Now, some of the math isn't exactly that easy once you start to put it back into the black hole physics. This is an area of black hole science or physics called black hole mechanics or black hole thermodynamics. There are 4 laws, just like you have your traditional laws of thermodynamics. Stephen Hawking, James Bardeen, and Carter helped develop that theory. I believe I got those names right. Yes, helped develop black hole thermodynamics. So this is talking about not just space-time as or relativity or black holes as a static entity. What happens when I take the mass of a black hole and I interpret it as a functional of the area of the event horizon, the angular momentum or spin around the black hole, right? And then the surface gravity of the black hole, right? How does the gravity itself across the geometry of the space-time, how does that disperse out? So those are some of the fundamental objects for a black hole. You can take a black hole and you only need 3 variables to describe a black hole. If you haven't learned anything today, learn this, write this down. You only need mass, area of the event horizon, and angular momentum to describe a black hole. They are some of the simplest objects in nature, but they require some of the most complex thoughts to actually develop the science behind them. So part of what I do in matching that to observation is what I develop things called spin currents in black holes. So we're talking about rotating black holes. We're talking about things spinning around them very rapidly. How do we match the right side of the equation for the matter energy content to the left side of the equation for the geometry of space-time? How are we matching those things together? I use concepts and constructs called spin currents. You can go read my paper that's on the archive right now and under review at Physical Review D, but about spin currents and how I'm using them for jets. And so that's more of how we are extending the theory, matching observation to theory, right? So this is, again, a little sample of some of my current work. I use data from Amigo X, the instrument that's going up later. XP just launched, giving us some polarimetry work from high energy schemes. And then I look at data from blazars. I use Fermi-Lat data, XP. I'm waiting for Roman to go up. We're using some James Webb data. So using a lot of different things here. And so I'm also on the new mission called the Event Horizon Explorer. So it's extending EHT, the Event Horizon Telescope, to incorporating a space-based component now. So now we can kind of look even deeper into a black hole, very, very close to the event horizon, to see how is the matter behaving there. If you'd like to follow my work, if you would like to send me questions, feel free to reach out. That's my social media handle, my email, my website, and we can now open it to any questions you may have that I see in the chat here. The chat's buzzing. But thank you for inviting me. And you've learned something today about black holes if you haven't already.
Thank you, Dr. Gamble. That was fabulous. So you're absolutely right. The question and answer section has lit up. So it looks like we've got 7 or 8 questions, which will give us just about enough time to get through. So, and looking at some of the names, I think we've got some folk with PhDs, possibly in astrophysics. I know that when we're in person at Keele, we also have junior and high school students. So there will be a mix of questions here. So I will start from the top and we'll work our way through. So David, thank you for sending in our first question. David asks, do the general relativity equations allow for, brackets, do they still work for more than 4 space-time dimensions?
Very great question, and they do. They work very well. I'll have to go down to 2 dimensions, 3 dimensions, 4 dimensions. They work very well in 5 dimensions. So we're talking about 5D space-time. They don't work too well once you start getting up above 5D. So in 6 dimensions, it gets a little shady. You have to do some mathematical tricks there, right? Add some fudge factors. But then again, in 7D, it behaves fairly well again. And then again, in 8-dimensional space-time interpretations, we can extend it up to 9. String theory operates in a maximum of 11 dimensions. So now, once you see those extra dimensions beyond 4, gives us a better operation or handling of the mathematics, as it will help to translate the physics that we see in nature, right? So anything beyond 4, according to our theories right now, there are what we are calling non-physical dimensions, right? So we can't actually go out and test for the 5th dimension, maybe. But as of right now, we only have 4 physical dimensions, and all the others help us handle the physics, help us handle the complex physics and math that we need to then channel down and make our interpretation or observations to our 4D spacetime. So great question.
Thank you, Ronald. Yeah, absolutely. Let's hope they continue. So Brian sends in the second question, which is as follows. In a rotating black hole where you showed matter is falling in and also being pushed out in a jet, does the matter pass what we think of as an event horizon between the incoming and outgoing parts?
So there is and I will, let me see if I can get back to my slides here. There's a region of, I'm going to go back here. So there's a region of space-time here, and you can see that the green, right, is kind of is what we call our outer horizon. So there's a region in between the outer horizon and that inner horizon, right, where matter actually threads through and it comes back out, but it has to come very, very close. It doesn't stay there long, and it doesn't go too deep. So you can think of it almost as like the crust of a black hole. You're kind of going in and then you're quickly coming back out, but it accelerates. But that is relative to the event horizon of a black hole. So another mathematical trick here, right? So another physical trick is that it doesn't actually cross the event horizon, the point of no return. It just gets very, very close to where, if you aren't moving fast enough, you are gravitationally bound to the black hole, right? So that is within kind of what we are calling another length parameter called our gravitational distance, right? There's a point where there's the event horizon, and then a little bit beyond that is what we are calling our area or region where you are gravitationally locked to the black hole. So at some point you will fall into or cross the event horizon, but it's a not yet area around the black hole. Hope that helps that question there.
No, thank you. That certainly helped me, actually. That was a really useful explanation. Thank you, Ronald. So that brings us on to a question from David, who asks, could you say something briefly about supermassive black holes and vacuum energy? I recently read that this contributes to the expanding universe.
Yeah, so let's... Yeah, so vacuum energy is kind of it is kind of a weird phenomena here. And I'm trying to see if I might have well, I don't actually mention any slide, but it's a weird phenomena where and it's kind of getting towards, I'll put this one up. It's kind of getting towards looking at dark matter, dark energy, right? So this is still using gravity to make interpretation of what we see or what we hope to see in nature. And there's another solution to Einstein's field equations that extend our regular interpretation of space-time and the geometry of space-time and the curvature that's involved to include the cosmological constant, or include that vacuum energy, right? So you're getting into a realm of cosmology called the lambda CDM model, right? So this is our lambda cold dark matter model, where we're talking about the relative expansion of space-time in the universe as in relation to our Hubble constant, right? So that is our numerical value that's kind of quantifying not only if our universe is expanding, but how fast is it expanding? And then if that changes, right, well, how fast is the change of the expansion of space-time changing, right? So our universe is not only expanding, but it's accelerating. So as you accelerate, as you move things apart in space-time, you've got vacuum energy fills the space. So you can really think of space-time, you can think of the universe as not having any empty regions of space-time. There may not be stars or galaxies or black holes there, but there is vacuum energy taking up that space, right? We've only seen 5% of the visible universe. So the other 95% we haven't observed yet is a little bit unknown. And so there's a lot out there that we've got to discover. Vacuum energy might be one of them that we might be able to see maybe 30, 100 years from now or something like that.
Fabulous. That maybe give some of our younger audience actually something to go hunting for, Ronald. So thanks for that. Yeah, which brings us actually nicely onto a question posed by Raven. And I think Raven must be an educator because they've asked, what are some beginner questions to pose to high school students to get them excited or thinking about black holes? So think of our younger audience. How can we get them all buzzing about black holes when they, certainly here in the England, when they all go on half-term break next week?
Yeah, so I would I'm gonna kind of go back here, right? So I really like these animations because it helps you to grasp the kind of the curiosity behind some of these things, right? So very early on, this is some questions that I had kind of in high school and in undergrad. I thought to myself, well, okay, if I were to actually approach a black hole, would it kind of look like a dark star? Would it look like some dark sphere in space? And would I be able to kind of interpret or see some little shadow if I look around it, right? If I could hold a black hole in my hand, per se, what would it look like? How would it feel? What would you see around it? You know, if you put your watch up to the black hole, what would your watch look like? Would it still tick? As you go closer and closer to it, it would probably stop ticking because time stops. Kind of at the centers of black holes as we cross that event horizon. So it's time slows down. It's time dilation. So that's some of the questions that you can kind of ask some of these students, and students can ask themselves, but fundamentally is, you know, well, what are some of the complexities? How curious can I be in asking these questions? What is dark matter? What actually is gravity? Where does gravity come from, right? So it comes from beyond what Newton is telling us because we don't have a quantum theory of gravity yet, succinct, testable theory of quantum gravity yet. What does the quantum realm look like for gravity? That's what the students can ask themselves because that's the next frontier. That's the new frontier in gravitational physics. It's quantum gravity. So it's, what does gravity look like on the quantum, very, very small scales, right? What does gravity look like to Ant-Man? That's the question that high school students can ask themselves. So I was at the Ant-Man and Quantumania movie premiere when it came out. It was a great movie. Go see it. It's coming out in a few days, actually tomorrow. But those are some of the questions they can ask themselves. You match it back to what you see in nature, what you see every day, right? What is gravity acting like in these environments?
Fabulous, yeah. And if we needed another excuse to go and watch a really cool film, that we can explore like the idea of going and do some physics in the theatre. That's great. Actually, that brings on nicely. So, if I'm right in thinking, Will sent a question, and Will's one of our younger audience members that normally turns up. So thanks for attending, Will. Will's asked a very direct question, which is, how fast is the jet versus the speed of light? So these jets that are being emitted, how fast are they in comparison to the speed of light?
Yes, so they are either we're looking at, so you have to look at kind of, you got to look at this kind of a outside in perspective, right? So we're looking at a jet, some of the slower matters towards the outside, some of the faster matters on the inside. We use what's called a Lorentz Factor in interpreting, quantifying how fast or energetic the matter is. So now for jets, the Lorentz factor is about a factor of 10, meaning that's not saying that it's 10 times faster than the speed of light. That's saying that it is within, you can approximate that to be proportional to about 10% of the maximum value for the speed of light. So we're talking about at least 90% the speed of light and higher. So we're getting very, 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 very close to the speed of light. If at like 99.99999% the speed of light. That's the Lorentz factor of about 10. 99.999, 3 decimal places. Some jets, some matter within jets are calculated to have Lorentz factors much higher than that. So they are 99.9999999% the speed of light. You may not think that these extra decimal places mean much, but in terms of relativistic physics, it kind of means the world. It means what physics we can use, what physics we can't use, and how we're using that physics to interpret what we see. So these things are moving incredibly fast. They are very energetic, which means they're very bright. And luckily, sometimes they point directly at us. Those are called blazars. So those are some of the objects that I see. We don't have to worry about jets impacting the Earth, where the one's not that close. So, but you can imagine a black hole kind of shining a flashlight at you, and you kind of collecting that light to see what it's telling you.
Brilliant, thank you, Ronald. Actually, that's answered one of the other questions, where should we be worried about future black holes in the Earth, which you've just answered. That's fabulous. So we can skip that one. But we will go on to a question from where's Robert's question gone? Robert's asked, does your work give any insight into quantum field theory for gravity?
It does, actually. It does a little bit. And so part of some of my work, and I'm going to jump back to my dissertation work that I did in grad school. Part of my work right now is kind of taking this macroscopic view, or this continual mechanics view of what we see that space-time and gravity and general relativity is doing, and shrinking that down. So then adopting the axioms and the theorems and things that we've tested in quantum field theory and applying that to gravity. What does it look like? What should it look like? And then also looking at, I'm gonna go here, looking at, right, some of the observations, some of the astrophysical observations that we see within jets. Jets is one of the best playgrounds for us theorists to look at in terms of quantum electrodynamics, right? So that's the quantum theory of electrodynamics. Thank you, Richard Feynman, for what's happening to electromagnetic matter on the quantum scale. That happens around black holes in these jets. That's the particles we're looking at. We're looking at photons, positrons, electrons, neutrinos. There's quark matter interpretations in there. And so we've got other astroparticle physics interpretations or observations of some of these environments. And we use quantum theory, right? We use very experimentally based interpretations or observation of quantum field theory, or evidence of quantum field theory, I should say. Some of the astroparticle physicists at NASA will try to correct me and say, well, no, it's evidence of quantum field theory. Well, I want the field theory in person, up close. And so that's kind of what we use. But again, there are some missing pieces to a quantum field theory interpretation of gravity. We don't know what gravity looks like on the quantum scale yet. We can't test for it. We don't have the technological advancement to do that yet. Hopefully we should have it. If the high school students, if the undergrads are curious, we'll get that in another 20 years or so, you know. But for right now, we are using our best bet, our best guesses on what the geometry is telling us, and to see, you know, what are the clues? What's nature giving? What are the clues that nature is giving us for a quantum theory of gravity?
Brilliant. Now, I am mindful of time, so thank you to everybody that's posed questions, because it's been fabulous. But I think 10 questions is probably going to be enough for Ronald. So I'm going to ask three or four more, Ronald, and we'll look to finish probably by 8:15. So apologies if we don't get through all of them, but I will try and there's a couple that are very similar, so we'll try and condense them. So the first one, again from Will, so thank you for sending this one in, Will. Very quickly, is what do the jets of this black hole consist of? So what is it physically or mathematically? What are these jets?
Very, very good question. We are still answering that question, right? So if we look at kind of this slide on the spectra for jets, they span the entire electromagnetic spectra, and even at higher energies for cosmic rays and neutrinos, right? And we have these other things called ultra high energy cosmic rays. And so it spans the entire electromagnetic realm. The actual particle content, as we say, within jets is obscured because they're so bright. We can't necessarily peer into the jet per se. So we have to use a combination of techniques. We have to match that with theory. We have to improve our theory or advance our theory based off of observations to kind of make more and more predictions of what we might see, right? So if we could turn the lights off on a jet to see what's coming out of the black hole or very near it, then we might be able to see, what's the matter constituents within the jet. Some things we can see based off of the interpretations or observations of the realms that's kind of outside the jet, right? We can also make interpretations of some of the geometry of magnetic fields within the jet, which then gives us clues to the matter content within the jet. But as of right now, we are still answering the question to give a definitive, concrete answer, right, of what exactly is inside the jet. We know it's baryonic matter, right? The matter that we see today. We know that's most of the content of the jet, but what else is in the jet? What else is in there? Is there dark matter in a jet? Who knows? There might be. But we're still answering that question of not just what's in the jet, but how is matter configured precisely within the jet, and how is it coming out? So those are some unknown questions in Aegean physics, or what we call the Aegean zoo. You can go look that one up too. It's a mind-boggling, it's a bonkers theory, but we call it the Aegean zoo by collecting all these different interpretations and observations of jets and quasars and blazars together.
Fabulous. I'm going to try and stick two questions together here, Ronald. But basically, we've had a number of questions about the speed at which these black holes spin, the regularity or the patterns that these black holes create. And unfortunately, it's anonymous. I can't attribute this to anybody in particular. But the question is, if the black holes was to spin fast enough, the question is, will they explode, or would they change that regular pattern that we see? So would anything happen to a black hole if it's continued to spin faster and faster and faster?
So absolutely, and I'm going to see if I can. I'm going to have to play this slide here. I'm going to see. Oops. I'm going to reshare this. And I'm going to stop it here. So that's the realm of relativity, pun intended, of kind of what might happen. And I say might because we can't see this, right? So this is a theoretical prediction of the geometry of space-time for the black hole, right? So this is the donut shape. And of course, there's a cutout here, so you can see kind of the interior structures there, but it would be completely closed. It would look like a torus. It'd be a donut shape. It'd have this little kind of curved features in the middle there, right, for top and bottom poles. But it would look like a donut. That is what we are calling a naked singularity. That is a black hole that has completely shedded its event horizon. So there's no more event horizon. There's no more other horizons, what we call a Cauchy horizon, right? Is where our causality or our cause and effect relationships for the logical or the philosophical questions for relativity comes into play, right? And then also we have other local cosmological horizons. We have to interpret these as large objects. So they may have cosmological horizons if they're on the size and scales of supermassive black holes. So if a supermassive black hole were to spin fast enough and it shed its event horizon, if you fell into the black hole before it spun this fast and then it spun that fast, you might be able to reappear into the universe again. You have a naked singularity. We don't know what's going on there. These are mathematical solutions. These are what the math is pointing us towards, right? So we're making our human interpretation, our human prediction to what might be a naked singularity. But mathematically, using what we've tested in relativity, that's what a black hole would look like if it completely blasted away its event horizon and it spun really, really fast. These are extreme speeds.
Thank you, Ronald. Right, and I'm going to keep it to the final 3 questions, but I think it will sum up your talk really nicely, actually. So, and the topics of those, we're going to talk a little bit about information paradox from Sarthak. We're going to have a question on frame dragging, and then it would be totally remiss not to talk about what next. So again, someone's asked about what can they do going forward. So Sarthak, thank you for this question. They ask, what significant developments are we making or have we made in solving the black hole information paradox?
So I'm going to go back here. Man, there was, gosh, and the paper completely escapes my mind, but there are a number of recent papers, and when we say recent in theoretical physics, we mean like the last 10 years. Last 10 to 20 years is recent for theoretical physics. Just to put that out there for timescales, right? So recent papers, there've been some advancements in our interpretation of the information paradox. And that is using an extended theory called the holographic principle, which states that if I have a configuration of matter, right? Entropy is really the variable or the entity that we're using there in thermodynamics. If I have entropy, what happens to the entropy of the matter as it crosses the event horizon, right? Got my event horizon. This matter has entities, got pressure, temperature, internal energy, all the thermodynamic variables. What happens when it crosses the event horizon? Well, that entropy kind of spreads, it smears onto the surface. The energy, part of the energy kind of smears onto the surface, and we might be able to see that smear. If we can peer close enough, we might be able to see that smear. This is, of course, highly theoretical, but Hawking did this in his early work. This is where we come up with Hawking radiation. This is where Hawking radiation comes from, right? So the holographic principle was based off of used parts of the Hawking radiation in terms of, well, if I take a positron-electron pair and I throw an electron into the black hole, but the positron gets kicked off, did the black hole lose some information? Did it lose information? Did it gain information? Did our known universe lose information? So there's a two-way street there. Did we just lose an electron? And did the black hole just lose a positron? So if the black hole stole our electron, then we stole our positron back. There is now it would then contribute to our asymmetry for the universe in terms of the matter-antimatter asymmetry. There is not an equal amount of matter to antimatter in the known universe. If there were, we wouldn't be here. Thank you, asymmetry, because they would both annihilate each other. So we're actually thankful that there's an asymmetry here. But where did that asymmetry come from? What happens when particle pairs separate at the boundaries of these black holes or the event horizons, right? So now, again, this is the earlier question of the quantum implications for black holes. This is where the quantum physics comes into play, because now you're talking about the physics for individual quanta of energy, right? Electrons, positrons, photons, quarks, neutrinos. We're talking about all those particles within the standard model here. In terms of what happens, do they fall in? Do they come out? Do we lose information? And how rapidly does that happen? On what time scale? Is the universe eventually going to evaporate? We don't know. But we've got very good interpretations. We've got very good predictions based off of theory. And as of right now, quantum theory is chugging right along. We can thank our nuclear physicists for testing all those things out and giving us some new insights to what's happening when you smash particles together and what's on the inside. There might be something inside quarks. Who knows? But that's that's what we use.
That would be an
Well,
interesting. That would be very interesting for some of our students to go and look at. Actually, have a think about what that
gluons
would be.
or what
Yeah.
you, this is the buzzword there.
Okay, so two
But
final questions.
mhm,
I appreciate time is scarce. So Alex has sent a question regarding frame dragging. So essentially, why
okay,
does frame dragging occur? If a black hole is spinning, why does that actually drag a frame around?
you're gonna need and I'm gonna go back here, right? So if I take, and I'm going to use my phone as an example, right? So if I take my frame, okay, and I put it in a static space-time, or I put it in a space-time that's not rotating, and I take my frame and I push it myself, so it's self-propelled. So you can think of a planet orbiting around a star, right? Self-propelled, right? There's a specific orbit. Okay, we're not involving any frame dragging. You will have a relative motion from that central object, the center of gravity, to that object that's rotating or revolving, orbiting around. I should say, words today, Lon. Orbiting around. Frame dragging, on the other hand, introduces curved space-time. Not only curved space-time, but it introduces the idea or the concept that gravity would induce an extra motion, an extra force upon that object to which it can no longer stop. It is forced to co-rotate with that central object. Because the gravity is so strong, it's forced to co-rotate with the object. So if you go back to our frame of reference here, right, our little spaceship, our spaceship in this static frame, right, is forced to accelerate around the black hole, even if you didn't have the thrusters on, even if you weren't moving, even if you weren't trying to swim through space-time, you would be dragged, you'd be pulled along and around the black hole in space-time. Now, another phenomenon happens is that your events in space-time start to stretch out. So if I or you were standing in front of a black hole, if you could, thought experiment here, and you experience frame dragging, if you went one full rotation, the light would be stretched all the way, the path of light would be stretched all the way around to the point where you might be able to see the back of your own head. That's frame dragging. That's what happens around a black hole. Light literally stretches all the way around, right? And so I think I had a nice picture for what you might be able to see here, right? So now, if I were standing here, this is a mathematical description, of course, but you can kind of see the branching that might happen. So now, this is all one structure. So we're not talking about closed loops anymore in space-time. We're talking about helical structures in how time evolves in this dragging of frames, right? So you might be able to look into the past or behind yourself if you were to stand in front of a black hole and you were to have your inertial frame dragged around. Interstellar is a very great movie for describing frame dragging. Go watch Interstellar. It was fantastic. The scientist that was on the ship, 30 years passed for him. The scientists that were down there on the planet, closer to the black hole, they were down there for 3 hours. That's frame dragging. That's relativity.
Fabulous. Thank you for that, Ron. That's excellent. We've got one final question, which I think will sum up beautifully where we're going with this, which is, and again, unfortunately, there's no name to this, but essentially the question is, how do I get involved in this? So if I've been inspired tonight by some of the research that you've presented, what opportunities, what experiences, what citizen science projects might a student here in the UK or over in the States, how can they get involved in this particular field of research?
Yeah, I would. So I would encourage you, and please don't shy away from what I'm about to say. But math. Learn all the math you can, because the mathematics as a scientific language, right? It'll take you very far. It will help you with interpreting the science or the physics that we see, it will help you interpret the observations that we see, but then it will also help you with learning the known physics for relativity. General relativity by itself is a very complex, very mathematically intense theory. And so learning the math intimately helps you learn the language better. So, you saw some German on the slides there. When I was in grad school, I learned how to read German so that I can have a different interpretation of some of Einstein's original papers there. And so that helped then again, using language to get a different interpretation of what I saw to answer the same question. Math is the same thing. We've got different types or different flavors of math to answer the same questions. So now to get involved in some of the science, where you study this in school, you take general relativity in undergrad, graduate, you take your astronomy courses. You don't necessarily have to be an astronomy major to study black holes. This actually is a very, very wide field of physics within physics majors. So this is coming from physics, not astronomy. So astronomers like to say, and some of my observational astronomer friends will kind of kill me for this, but they like to say that they are theorists for studying black holes. I'm like, oh, you guys are, yeah, okay. But there are mathematical theorists, I will say, or hard theorists that study the mathematics behind black holes and what that entails. So that's how you can get involved. Go read Myers, Northorn, and Wheeler. Anybody can go pick it up. You can reach out to me and I can send you some resources where you can find these things, what to read, what subjects to read up on, if you want to get a broader knowledge on black holes. And then I encourage you, get involved. If you're in the UK, get involved in ESA, European Space Agency, and the LISA project. Get involved in some of the observational missions that are out there. Athena, I believe, was one of them also. And if you're in the US, there's NASA right here. NASA's in your backyard. So if you're in undergrad, graduate school, postdocs, I encourage you to apply to all those things. You can be an international postdoc at NASA Goddard. Some of my friends are from the UK and from Italy, from all over. You can be an international postdoc and do this work. And so it's not gatekeep to just American citizens or anybody else. Anybody can do this. Anybody can study this. You don't have to be a math whiz either. So you can definitely study this, and it takes a while, but it's a humbling science, I would say.
Thank you, Ronald. I think, yeah, that is a beautiful way to finish it. It's accessible if you want it. The opportunities are there, and it's and without sounding cliche, it is a very energetic field. I can see from what you've presented tonight, there's a lot going on. It's not like some areas of physics where not a lot of movements happen for 50 or 60 years. So fabulous. So on behalf of and Sharon's just told me 118 people attended tonight. So on behalf of everybody that's attended this evening, wow. I just wanted to say incredibly thank you very much for your time, Ron. I really appreciate it.
Thank you.
Before everybody goes, just to remind you that we have 2 further talks in our program left this year. A month today, on the 16th of March, we've got Dr. Tianning Zhu, who's going to be talking all about electric vehicle charging. So from the macroscopic to the probably microscopic, a very local, very topical issue here in the UK at the moment. And then we finish up on the 20th of April with Dr. John Mansfield, again from the University of Michigan, talking about applications of microcharacteristic applications to cultural artifacts. So we really have covered almost every field of physics this year, ladies and gents. So thank you very much for your time. Thank you again, Ronald, for an excellent talk. It's been fabulous.
Thank you. Thank you.
Have a lovely evening if you are here in the UK. Have a lovely day or afternoon if you're in the States. And we look forward to seeing you again very soon. Thank you and good night.